Hello. How are you doing today?
Good morning.
Right. All right. So let's see. In terms of meetings this week, we had DevoWorm, and that was a discussion on some proposed work on hypergraphs and how that might apply to C. elegans and biology more generally. Going over some of the different kind of meta aspects of that, some of the ways in which you implement hypergraphs and things like that. And then we also talked about centential cells and C. elegans and how to think about the lineage tree. Centential cells are cells with multiple nuclei and a single cell body that's connected through cytoplasm. So there are a lot of instances of that in the C. elegans phenotype, but in other phenotypes as well. Yeah, so that was DevoWorm, and that's the only other meeting we had this week, once again. As for our open source meeting, I'm not sure when we'll start that up again. Maybe at the first of the month or in that week. So whatever Friday that is, first Friday of May, we might do that. But we'll see. And around that same time, of course, we have the Google Summer of Code selections. So we don't make those public usually until the announcements are made by the program. So that's right around the 1st of May, usually like the 3rd or 4th of May. So that's coming up, and hopefully we get the people we want. Sometimes we don't get every slot that we want, but that's okay. We make do. And so in years past, we've had more, and it always happens, we have more applicants than we have spaces for. We get allotted a certain number of slots by the program, and then we have to select the highest rated proposal. And sometimes it's what we want to do over, what makes sense kind of for us, as opposed to, any other kind of direction. And so that all goes into the decision. So if people aren't selected, they're perfectly welcome to join us and try to do that project as part of our open source group, which we've done in the past. Last year we had one person do that, the person who was working on reinforcement learning. And so, we can always accommodate that for people as well. Okay. So if you, good luck to everyone who applied. And we'll see what the outcome is at the beginning of May. All right, so last week we talked about this paper, Meta-Learned Models of Cognition. And this was a paper where we were introduced to this model of meta-learning, and we went through all the Bayesian rules and things like that, and thinking about how one can apply Bayesian methodology to meta-learning. We also talked about some of the other ideas they had for this. So they had these 4 different arguments for meta-learning. So they had the computational intractability argument, the inference problem, the ability to manipulate a learning algorithm's complexity, and then they had these neuroscientific insights. This was where we left off, roughly. And we were talking about this rational analysis of cognition. So this isn't just useful for artificial intelligence. This is useful for understanding cognition. And so they were talking about rational analysis of cognition. They were making connections with reinforcement learning, which will become important for today. And they're talking about a number of other types of interesting questions or directions. So they have this paragraph here. So they say, we place an emphasis on the second aspect in the present article and advocate for using fully converged meta-learning algorithms as replacements for the corresponding Bayesian models for rational analysis of cognition. So they're actually not using like a Bayesian model per se. They're using an analog of the Bayesian model. And they're building an algorithm that's based on the Bayesian model. And then they're going to have those models, let them run to convergence and then make statements about cognition and about intelligence and all that. Okay, so that's where the rest of the paper goes. However, it is important to mention that we believe that meta-learning can also be a valuable tool to understand the process of learning to learn itself. So this idea of learning to learn is the key here. So we talked about the Bayesian method as being this sort of, y given x situation where it's conditional probability. So, or conditional likelihood is more what they're kind of getting at. So, if I have one thing that's true, what's the likelihood that this other thing will be true? And, you think about coin flips where you flip a coin. And in the frequentist approach, you have this flipping of the coin, and the probabilities that you get are all independent of one another. And it assumes that there's an independence of that process. So every coin flip is independent of every other coin flip, and you get a probability of 0.5. And so that's the sort of frequentist view. In the Bayesian view, you might have some conditional probability or conditional likelihood. That is, that the outcome of a coin flip is dependent on the outcome before. So, this is particularly handy if you have a run of heads, and then, we can make a statement that says the likelihood of heads coming up again is a certain amount given the past outcomes, and the likelihood becomes lower and lower as we get deep into the run of heads, and then finally we get a tail, which becomes more and more likely. Now, things like that. So we're looking at patterns within our time series, patterns within the structure of the system we're trying to predict, and we're finding things that may be, conditional. That it's less likely that we have an outcome happen 40 times in a row. And we have a statement to make we can encapsulate that in a mathematical statement. Okay, so that's a little bit about that. In the next section, we will outline several arguments that support this approach. However, it is important to mention that we believe that meta-learning can also be a valuable tool to understand the process of learning to learn. Okay. In this context, several intriguing questions arise. The first one is, at what time scale does meta-learning take place in humans? So we talked about our time scales from last time, where we have things happening at the millisecond level. We have things happening at the seconds level, the minutes level, at the hours level, and at the days level, and maybe even at the years level. So we have, some sort of cognitive event or some sort of stimulus, and that gets processed rather quickly within maybe several hundred milliseconds. And we can measure that with EEG or some other electrophysiological thing. And then we have things that happen at seconds or minutes, which could be, reciting a poem or having a discussion during a coffee break, or, practicing riding a unicycle or something like that, which we might be into, minutes to hours. And then we have short-term memory, which of course are things we hold in a short-term memory store and access as we do those kinds of things. And then we have long-term memory, which encodes things for long-term storage. And then, we have hours and years then, which are sort of historical memory or reproduction or other things like that. We also have naturalistic cognition, which is this continuous stream of activity, and those can take place at multiple time scales. So where does meta learning take place in that? If you have meta learning, if you have something like, if you learn how to, say, ride a unicycle, or you have a conversation with someone and you learn some interesting fact and you maybe put it in short-term memory, and then that gets encoded into long-term memory. And then you maybe have this process of meta learning where maybe you learn several interesting facts during that conversation. You remember all of them in long-term memory, you encode them. Does meta learning take place then? Or does meta learning take place much more in a much more expedient way? In other words, do you do sort of online meta learning as you encounter facts in the world? So if you see something new, you just kind of synthesize it with what you knew previously. You recall some memories, and then you make this new inference. It's basically y, which is this new experience, given x, which is the previous experience. And that gives you this meta learning prior, basically. Okay, so that's the first question. The second question is, how much of it is due to task-specific adaptations? So is meta learning a sort of a thing that we learn, a thing that we adapt to? So if we are in an environment of learning, do we have this sort of adaptation that is basically meta learning? So in other words, is it if we do something like learn how to use a computer, is that sort of, do we use meta learning as an adaptation to improve that process? Or if we learn how to play a stringed instrument, do we use meta learning to improve performance in that process? Number 3 is, how much of it is based on evolutionary or developmental processes? So, do we have, is meta learning sort of embedded in development or in evolution? And again, those time scales become important, because development is this, sometimes years-long process. Evolution is many, many years. So, it's generational. And so how does meta learning unfold there? So that's another question. And so those are 3 questions that they bring up. While we agree that these are important questions, they're not the focus of this article. Okay, but those are good things, I think, to frame everything under and understand kind of what the consequences or what the outcomes of meta learning are. Okay, so in part 2 here, why not Bayesian inference? So again, they do a lot of introduction of Bayesian modeling, and they use this sort of way to think about it. And of course, the sorts of algorithms they want to use, the sort of brain-inspired models they want to use, but the Bayes rule and the Bayesian approach is important in how that's structured. But why not just use, Bayesian inference directly? So we have just argued that it is possible to meta-learn Bayes optimal learning algorithms. What are the implications of this result? Bayesian inference has already established itself as a valuable tool for building cognitive models. We have a lot of cognitive models that rely on Bayesian inference. In this section, we provide 4 different arguments that highlight the advantages of meta-learning for building models of cognition. So this is where, again, I don't know if they're conflating, well, they're not conflating Bayesian models, but they're kind of zooming out and saying, uh, we're really interested in meta learning, but we can use Bayesian inference to best understand meta learning. So many of these arguments are novel and have not been put forward before, and so their arguments are as such. The first is intractable inference. So this is the first argument: meta learning can produce approximately optimal learning algorithms, even if exact Bayesian inference is computationally intractable. So we can have sort of we can use Bayesian inference, maybe not as a exact solution, but as an approximate solution. And we can have this sort of meta learning as the outcome. So we can, if we use a meta learning approach, we can produce approximately optimal learning algorithms. So we don't have to have the exact Bayesian solution. We just need to sort of have take an inferential approach, and meta learning will get us there. Here's an important point. Meta-learned inference also never requires an explicit calculation of the exact posterior or posterior predictive distribution. So when we talk about something that's meta-learned, learned from previous evidence, and synthesizing that, we don't really need to calculate out an exact posterior predictive distribution. Remember, we're doing inference in the following way. We have this prior distribution, we have observations, and then we have this posterior distribution, which is predictive. And so what does meta-learned inference do? It performs approximately optimal inference via a single forward pass through the network. Inference in this case is approximate because we have had to determine a functional form of the predictive distribution. The chosen form may deviate from the true form of the posterior predictive distribution, which in turn leads to approximation errors. So basically, they try to get it as close as possible, and then if they don't get it as close as possible, you have these approximation errors, and then you try to minimize that error. So that's basically it. And then the second argument is that meta-learning can produce optimal learning algorithms, even if it is not possible to phrase the corresponding inference problem in the first place. So in other words, if we can't define the exact inference problem, if we can't state the problem in exact terms, we can still get optimal learning algorithms from meta. It's hard to pose an exact problem, which means in Bayesian inference terms, you need to be able to specify a prior and a likelihood. So you need to be able to specify the prior distribution, then take those observations and produce a likelihood that is reasonable. So that's basically what we're doing. So it's, you have to have that well defined in order to have a shot at getting something decent out of a Bayesian inferential approach. If we turn to Bayesian decision theory, Savage, in 1972, made the distinction between small and large world problems. A small world problem is one in which all relevant alternatives, their consequences, and probabilities are known. So that's where we have something that's exactly defined, but also is a rather small problem where we can get our hands around the probabilities and the consequences, basically knowing all of the outcomes. And so that's a small problem, I guess. And this is contrasted with a large problem, or a large world problem, in which the prior or the likelihood cannot both be identified. So you can't necessarily get a good prior distribution because there are a lot of observations in the past that we can't access. We also can't access the likelihoods because there are a lot of things we can't directly observe. So that's a large problem, and it's very hard to define what the prior looks like and what the corresponding likelihoods look like. So number 3 is resource rationality. And it's stated as meta-learning makes it easy to manipulate a learning algorithm's complexity and can therefore be used to construct resource-rational models of learning. So this is where we have meta-learning. It can manipulate the learning algorithm's complexity itself. And so then we can construct resource-rational models of learning. Cover, in 1999, put forward a dichotomy that will be useful for our following discussion. He refers to the algorithmic complexity of an algorithm as the number of bits needed to implement it. By contrast, he refers to the computational complexity of an algorithm as the space, time, or effort required to execute it. So it's implementation and execution. It is possible to cast many approximate inference schemes as resource-rational algorithms. So this is a specific type of algorithm. The resulting models typically consider some form of computational complexity. So in MC methods, which is a specific type of method we can use, and Bayesian learning and inference is important in MC methods. Computational complexity can be measured in terms of the number of drawn samples. Drawing fewer samples leads to faster inference at the cost of introducing a bias. So this is where we have this sort of sampling process. We draw a certain number of samples and we get our prior. And so we can do this quickly. We can do this sort of, for certain problems where we might need a fast answer, or there's just so much data that we can't reasonably sample all of it. We can do that. We can get faster inference, but we get a bias in the data. We might sample from a certain part of the distribution unevenly. In variational inference, on the other hand, it is possible to introduce an additional parameter that allows us to trade off performance against the computational complexity of transforming the prior into the posterior distribution. And so other frameworks for building resource-rational models, such as rational meta-reasoning, can also only target computational complexity. Okay. So I'm not going to get too much more into these type of models, but just suffice it to say that MC models fall into that category. Variational Bayes falls into that category, and so forth. This idea of computational complexity is interesting, because in algorithmic complexity by extension, because a lot of times, we have problems that are of different varying complexities, and it's worth, I think, thinking about that. I don't think people talk about that enough in a lot of especially the applied machine learning literature, but especially just thinking about different types of computational problems, especially related to cognition. Then argument 4, which is neuroscience. And that argument is meta-learning allows us to integrate neuroscientific insights into the rational analysis of cognition by incorporating these insights into model architectures. So now we're getting from sort of Bayesian inference, the sort of details of that, to computational complexity, and now to sort of the architecture itself, which is it's biologically inspired. In addition to providing a framework for understanding many aspects of behavior, meta-learning offers a powerful lens through which to view the brain structure and function that we're interested in. For instance, Wang presented observations supporting the hypothesis that prefrontal circuits may constitute a meta-learning reinforcement algorithm, or a Meta Reinformcement Learning system. This is where we're getting into reinforcement learning, because, of course, reinforcement learning happens in the brain as well as a computational process. We have examples of reinforcement learning in neuroscience, And I suspect that's kind of where they're headed with the reinforcement learning aspect. That you can build these circuits or these, I guess, architectures that mimic circuits that implement reinforcement learning. So you have these meta reinforcement learning systems. From a computational perspective, meta learning strives to learn a faster inner loop learning algorithm by an adjustment of neural network weights and a slower outer loop learning process. Within the brain, an analogous process plausibly occurs when slow, dopamine-driven synaptic change gives rise to reinforcement learning processes that occur within the activity dynamics of the prefrontal network. This allows for adaptation of much faster timescales. So we have two things here. We have sort of this circuit that we can use as inspiration for a system that basically has a set of feedback loops in it. So you can reinforce learning easily with feedback loops. You can actually enforce meta learning with feedback loops as well, because you have these prior experiences which allow you to build a prior distribution. And then you have reinforcement of that prior distribution by observations, by the current state of that circuit. And then you have an ability to build sort of representations that are well supported by reinforcement versus representations that are not. And then that gives you meta learning. So you have this faster inner loop learning and this slower outer loop learning. The faster inner loop learning may be where you actually reinforce the things that you maybe observe once. Have you observed them again and again, they become sort of inscrutable, or they become undeniably true, I guess. Or you might just see them a lot. And then slower outer loop learning might allow you to build a model of meta learning. That is, what have I learned and how does it fit together? Or what is it, how do I distinguish between different alternatives that I've learned? So, all of this sort of is to say that you have this architecture that can be described in sort of this Bayesian model, and it can also operate as this learning and meta learning system. Within the brain, an analogous process plausibly occurs. Okay, we did that. All right, so we are able to have an adaptation on much faster timescales. This perspective recontextualized the role of dopamine function in reward-based learning and was able to account for a range of previously puzzling neuroscientific findings. So this is where they talk a little bit about the neuroscience of reinforcement learning and meta reinforcement learning and so forth. Importantly, the direction of exchange can also work in the other direction, with neuroscientific findings constraining and inspiring new forms of meta learning architectures. So, for example, in this resource, Rohira et al. 2018 showed that recurrent networks of spiking neurons are able to display convincing learning-to-learn behavior, including in the realm of reinforcement learning. Episodic meta reinforcement learning, which is Rohira et al. 2018, these type of architectures are also heavily inspired by neuroscientific accounts of complementary learning systems in the brain, which is covered by McClellan, McNaughton, and O'Reilly, 1995. Both of these examples demonstrate that meta-learning can be used to build more biologically plausible learning algorithms and thereby highlight that it can act as a bridge between MAR's computational and implementational levels. So, if you remember MAR's 3 levels, you know that 2 of those levels are computational and implementational. Okay. Finally, the meta-learning perspective not only allows us to connect machine learning and neuroscience, via architectural design choices, but also via the kinds of tasks that are of interest. So, functional specialization in neural circuits, which has been widely observed in biological brains, arises spontaneously as a consequence of task demands. Convolutional neural networks, trained on both face and object recognition, depicted emergent segregation on the basis of these tasks. So we get this sort of emergent cognition from this meta learning system. And so they go through some things about meta learning models. They talk about them a little bit more. They talk about language as well, inductive biases, which are important, model-based reasoning, exploration, which is also important, cognitive control, and then the question, why is not everything meta learned? So why don't we just use meta learning for everything? So meta learning, of course, is a useful tool for constructing cognitive models, but it's important to note that we do not claim that meta learning is the ultimate solution to every modeling problem. Instead, it is essential to understand when meta learning is the right tool for the job and when it is not. So they give some examples of why it's not always the best way to look or to implement a learning system. The first is lack of interpretability. So the most significant detriment is that meta learning never provides us with analytical solutions that we can inspect, analyze, and reason about. So this is where we have this distinction between Bayesian exact Bayesian models and meta learning. So take as an example the data generating distribution we encountered earlier. For these assumptions, a closed form expression of the posterior predictive distribution is available. By looking at this closed form expression, researchers have generated new predictions and subsequently tested them. Performing the same kind of analysis with a meta-learned model is not as straightforward. We do not have access to an underlying mathematical expression, which makes a structured exploration of theories much harder. So I guess one of the differences then between the meta-learning and the sort of the approximate Bayesian model is that you're just really basing your answer, your final sort of way that the algorithm is implemented on sort of the structural similarity and not necessarily following a mathematical model directly. So in other words, there's something like a prior distribution, there's something like observations, there's something like a posterior distribution. It's not even that it's being estimated, it's that it's being kind of implemented in real terms. So Bayesian models are of course highly theoretical in terms of their mathematical abstraction, but implementing them in the real world, of course, is a little bit different. Okay. That being said, there's still ways to analyze a meta-learned model's behavior, and so we can do this. We don't have full interpretability. We can't account for every component. Like we couldn't say how meta learning arises directly. We can't say that this is the likelihood that led to this outcome. But we can, sort of analyze a meta learned model's behavior. But we can also, take these kind of black box models and use tools from cognitive psychology to analyze what's going on. So we can treat models as participants in a psychological experiment, have them perform tasks, and then collect the data and analyze it accordingly. So that might be a way forward, is to just have our meta-learning models produce output, behave in the real world, and then measure what they're doing and see how that looks. You might even get a number of model implementations and then, have them as like a study where you have a number of subjects where you're all training on the same task. We Okay, so there's also intricate training processes. So when using the meta learning framework, one also has to deal with the fact that training neural networks is complex and takes time. Neural network models contain many moving parts, like weight initializations or the used optimizer, that have to be chosen appropriately such that training can take off in the first place. Training itself may take hours or days until it's finished, so this is part of this timescale issue. When we want to modify assumptions in the data generating distribution, we have to retrain the whole system from scratch altogether. Thus, although the processes of iterating over different environmental assumptions is conceptually straightforward, it may be time consuming. Bayesian models can, in comparison, sometimes be more quickly adapted to changes in environmental assumptions. Okay, so basically, let me assume I wanted to explain human behavior through a meta-learned model that was trained on the data generating distributions and these equations, but found that the resulting model does not fit observed data well. So a lot of times your model won't fit the observed data. And so, this is something that you have to generate alternative hypotheses for. And ultimately that can hurt you if you're just using a strictly Bayesian interpretation. If your prior represents a hypothesis, and if that hypothesis doesn't fit the observations, then your likelihoods aren't going to be very accurate. So this is where we have this difference between meta-learning and sort of the strict Bayesian representation. There is furthermore no guarantee that a fully converged meta-learning model actually implements a Bayes optimal learning algorithm. While we are able to compare it to analytical solutions for simple cases, like our insect length example, which we talked about last week, where they measured the length of insect body parts and they tried to predict species and things like that, it is generally impossible to verify that a meta-learned algorithm is optimal. Indeed, there are reported cases in which meta-learning failed to find the Bayes optimal solution. We believe the issue can be somewhat mitigated by validating meta-learned models in various different ways, but ultimately future work should come up with techniques to verify meta-learned models. So then, in summary, they have this question, and this is the thing that's been bothering me, I think, throughout the paper, is they kind of swap out meta-learning and Bayesian inference. And they're not the same thing. We can base our meta-learning on Bayesian inference. We can model it after Bayesian inference. But it's not, they're competing frameworks, basically. And so, this is something that we can look at their different strengths and weaknesses. We can use like a strict Bayesian form of Bayesian inference. We can use a meta-learning model. But they argue that the meta-learning framework does not and will not replace Bayesian inference, but instead will complement it. It broadens our available toolkit and enables researchers to study questions that were previously out of reach. And then they basically kind of get turned just to meta-learning and talk about domain general models of human learning. What does the future hold for meta-learning? The current generation of meta-learned models of cognition is almost exclusively trained on the data generating distribution of a specific problem family. While this training process enables them to generalize new tasks inside the problem family, they are unlikely to generalize to completely different domains. We would, for example, not expect a meta-learned algorithm to perform a challenging maze navigation task if it was only trained to predict the lengths of insect species. And so this turns to sort of the basis for cognitive modeling and domain-specific modeling. And they agree with Newell circa 1992. This is some of the earliest work on the Sora architecture, where they're actually were looking for not to build a cognitive architecture, but to build these unified theories of cognition. And so this is one of the points here is that, we build cognitive architectures. We build these things to learn about cognition, not necessarily to simulate things. We want to simulate things. We want to build like an artificial form of cognition, and that's interesting. But we also want to build theories of cognition from those models. So we agree with Newell that unified theories of cognition are the only way to bring this wonderful, increasing fund of knowledge under intellectual control. Ideally, such a unified theory should manifest itself in a domain-general cognitive model that can not only solve prediction tasks, but it's also capable of human-like decision-making, category learning, navigation, problem-solving, and so on. We consider the meta-learning framework the ideal tool for accomplishing this goal, as it allows us to compile arbitrary assumptions about an agent's beliefs of the world and its computational architecture, and combine both of those into a cognitive model. Okay, so that's, I think, enough on that paper. So that was this paper here, Meta-Learn Models of Cognition. So I wanted to go over that, the second part of that. I thought that was important for kind of motivating the other things I wanted to talk about today. So yeah, I think it's an interesting paper. Like I said, I think I don't want to say they conflate meta-learning and Bayesian inference. They're approaching it from the standpoint of looking at Bayesian inference as something that we do in various contexts. And we kind of understand how to build algorithms around that. And then comparing that or contrasting that with things like meta-learning models, where we're learning to learn. Where the structure is similar, you can implement Bayesian inference in meta-learning. But at the end of the day, meta-learning may be different meta-learning techniques, whether or not they're Bayesian, whether or not they actually implement Bayesian inference is, in the way it's defined mathematically, is the question. So I wanted to move on to another set of, I have 3 other papers here in this group. And this next paper then is, I think this was also in the Slack. I think VD also put this in the Slack. I think it was in the Bayesian, or in the Gutenberg Vehicles channel. Yes, okay. And so this is it was a conference paper from 2023. And this is learning meta representations for agents and multi-agent reinforcement learning. So this is, again, kind of focusing on reinforcement learning. So like in the last paper, we talked about Bayesian inference. But we also talked about reinforcement learning. And so meta-learning involves this sort of reinforcement, this sort of observing prior things that happened in the past, and then observing the world now, figuring out what's important. Then those get reinforced in a posterior distribution, and then that's kind of how you implement meta-learning. So that's basically the approach that we saw in the last paper, and you can follow that out, and you can build an algorithm around that. This is where you're building meta representations for agents. So this is where they have to learn those representations. So the abstract reads, in multi-agent reinforcement learning, the behaviors that agents learn in a single Markov game, which is MG, are typically confined to the given agent number. Every single Markov game induced by varying the population may possess distinct optimal joint strategies and game-specific knowledge, which are modeled independently in modern multi-agent reinforcement learning algorithms. In this work, our focus is on creating agents that can generalize across population-varying Markov games. Instead of learning a unimodal policy, which is, of course, there's a distribution there, each agent learns a policy set comprising effective strategies across a variety of games. So we propose meta representations for agents, or MRA, that explicitly models the game common and game-specific strategic knowledge. So this is where you have different types of knowledge. You have game common knowledge and game-specific knowledge, or game-specific strategic knowledge. By representing the policy sets of multimodal latent policies, the game common strategic knowledge and diverse strategic modes are discovered through an iterative optimization procedure. We prove that by approximately maximizing the resulting constrained mutual information objective, the policies can reach Nash equilibrium in every evaluation Markov game where latent space is sufficiently large. When deploying meta representations for agents in practical settings with limited latent space sizes, fast adaptation can be achieved by leveraging the first-order gradient information. Extensive experiments demonstrate the effectiveness of MRA, or meta representations for agents, in improving training performance and generalization ability in challenging evaluation games. So this is quite technical in the sense that it's kind of hard to follow where they're going with this. So a Markov game, if we can find out what that is exactly. Okay. So we start here. Behavior of agents learned in a single Markov game, highly dependent on the environmental settings, especially the number of agents, such as population. Many multi-agent reinforcement learning, or MARL algorithms, are developed in games in a fixed population. And so sometimes we have problems with generalization in settings like this, which is where the policies learned in a single Markov game are brittle to the change of agent number. Recent works have experimentally shown the benefit of knowledge transfer between Markov games at different populations, which is required to perform between successive games. In this work, we are concerned with learning multi-agent policies that generalize across Markov games. And so let's see if we can find out what a Markov game is. Okay. For games induced by varying the population, the distinct optimal policies are determined by different strategic relationships between agents, which we characterize as game-specific knowledge. For example, in a Pac-Man game that is populationally dominated by ghost agents, the game-specific knowledge for Pac-Man is to focus on the ghost agent's positions for survival. However, as all Pac-Man agents ignore other Pac-Man agents' positions, they are unaware of collaborating, and their ability to collect food dots in evaluation games is poor. So one example they give is Pac-Man. So a Markov game is essentially where you have agents that use this sort of Markov model to model their behavior. So in Pac-Man, the ghosts have this sort of repertoire of behaviors, and they're implemented using a Markov chain. And then the Pac-Man agents, of course, could collaborate and have a coordinated strategy, but they don't. So, this is where this affects the knowledge of the game or what you need to know to play the game. So you have to know, for example, that the ghosts are going to behave sort of randomly. You also know that you're not going to be able to collaborate with your other fellow Pac-Men to get an advantage in the game. So that conditions the different strategies that are employed. One potential fix is to learn the representations which can serve as the game common knowledge and generate a set of policies that output the best effort actions when conditioned on different suboptimal strategic relationships between agents. So this may force Pac-Men to pay more attention to other Pac-Men in spite of the game being ghost dominated. Although these policies can be suboptimal in the training Markov game, they have the potential to perform well in the evaluation games in a zero-shot manner. This motivates us to learn diverse strategies so that even if not all knowledge variations are covered during training, the game common knowledge can be learned. So you want to be able to train agents on all of the things that they might see. And so this is where you get, you want to learn as many strategies as possible. So you have this game common knowledge, which is, okay, there's something like this that you might encounter. And so you might not be able to learn a specific variation of a rule, but things are very similar to that. Better generalization is thus achieved since we only need to fit the best strategic relationship in the evaluation game. So this is kind of the intuition that they're coming into this. So they're formalizing this by proposing meta representations for agents, or MRA, to discover the underlying strategic structures. So you basically want to learn how the game is played. It's like if I tell you the rules of a game, that will tell me how strategies will be implemented. I mean, strategies will be implemented within the framework of those rules. If I learn the rules of the game, I can kind of figure out what kind of strategy might be employed. I know basically what strategies won't be employed. And so from there I can sort of build. But it's not just learning the rules of the game. You're learning other things. You're learning potential solutions, and you're learning other attributes of the environment. Specifically, by meta-representing the policy sets with a multimodal latent policy suite, they gain common knowledge in diverse strategic modes are captured through the iterative diversity-driven optimization. We prove that by approximately maximizing a constrained mutual information objective, the latent policies can reach Nash equilibrium in every evaluation game if with a sufficiently large latent space. When deployed in limited-size latent spaces, fast adaptation is achieved by leveraging the first-order gradient information. We further empirically validate the benefits of MRA, which is capable of boosting training performance and extrapolating over a variety of evaluation games. So they give a mathematical definition of a Markov game. An N-agent Markov game, M, is defined by the state space S, action sets A1 through AN, and observation sets O1 through ON. So we have observations, we have actions, and those are two sets that operate in a state space. For any agent I included in 1 to N, OI included in OI, is an observation of the global state S. The state transition and reward function for agent I are defined in this term, and they're defined as this interval from 0 to 1, respectively, where delta S denotes the set of discrete probability distributions over S. The joint strategy, then, is denoted as pi 1 to pi n, where pi I is the strategy of agent I, and pi negative I is the joint strategy excluding it. So you have this joint strategy, and then you have joint exclusion. So you have like these overlapping, you have basically this Venn diagram and then the exclusionary area of that Venn diagram. In the following sections, we study the Markov games with discrete states and action spaces. So something like, I guess like Pac-Man would be a good example, where you have an action space and discrete states, and you define it in terms of these joint strategies and disjoint strategies. In this work, we consider the role-symmetric Markov games, where homogeneous agents are with the same reward function and action space. So they're the same, you can have, I guess, heterogeneous agents where they have different reward functions and different action spaces, but in this case, we're training them all in the same sort of world. So we could roll asymmetric Markov games, I guess, but they don't want to do that. It's too complex. The number of types of homogeneous agents is denoted as H. So, for example, an agent of value 2 in an N-agent Pac-Man game representing Pac-Man and the ghost agents. So you have, I guess you would have 2 types of agent. So you have Pac-Man and you have the ghosts, and they have different reward functions and action spaces. Homogeneous agents are symmetric in each game. Changing the policy of an agent with another homogeneous agent will not affect the outcome. So if we swap out Pac-Man or ghosts, they basically follow the same rules. Population varying Markov games, including training and evaluation Markov games. In other words, varying N1 and N2, where you have Pac-Man and ghosts, are with the same H in the states from states at S, or is described by different transition and joint space observation, action, and reward functions. Then we have this relational representation. So this is an opponent modeling framework called relational representation, and citations are here. This aims to capture the strategic relationship between agents and output and embedding E for further policy and critic function learning. So basically, we're trying to get this set of relationships, output and embedding, and then use that for further learning. So maybe meta learning or something like that. Specifically, consider the observation OI of agent I with entities O of I, where OIS is agent I's self-properties. It's, for example, its speed. OIJ is agent I's observation of agent J. So you can have agent I can have self-properties, it can measure its own speed, it can observe agent J and its behavior, and then have these sort of observations of environmental information, such as landmark locations. And all of those can be concatenated into a single observation. So that's the first part. And then with self-attention, generating the pairwise relation, GIJ, which is the jth entity of agent I, with its egocentric relational graph G by. The representation embedding EI for agent I is formulated in this equation here, where we follow the transformer architecture, and that represents our linear function. The observation embedding with an arbitrary number of agents can thus be represented with a fixed length. Then they have Nash equilibrium, and they talk about that. So every agent in the Markov game M acts according to the joint strategy pi at state S, the value of agent I, and the expectation of I's discounted cumulative reward. So this is in Nash equilibrium. A common metric to measure the distance to a Nash equilibrium is Nash conv, which represents how much each player or agent gains by deviating from its best response in total. And it can be approximately calculated in small games. We denote Nash conv of pi in the Markov game. M is dm pi, defined this way. And so with this definition, the joint strategy pi reaches Nash equilibrium in M if and only if dm pi equals 0. So that's basically what they're defining. They're basically defining the Markov game mathematically, this relational representation, which is some sort of, I guess, a meta representation that we can use for further evaluation, and then defining things in terms of Nash equilibrium. Okay, so in a single Markov game, achieving Nash equilibrium gives reasonable solutions and is of great importance. To enable generalization in different Markov games, the most straightforward way is to learn a joint strategy set that contains effective joint strategies for each Markov game. We denote the set of all training Markov games as M, and the set of evaluation Markov games as M prime. Then the goal is to learn an optimal joint strategy that satisfies certain constraints. And they have the relational representations. So this is sort of the implemented architecture of the MRA algorithm, where you have self-attention, you have the decentralized actor, these different strategies, and then the centralized critic, which is used to reinforce those strategies. So you see, you have this actor-critic learning, where you have the actors that are performing the strategies, this meta-representation, which is the critic, that's reinforcing the strategies, and then together that's used to produce this outcome. Unfortunately, although the above design fits well into the multitask MARL setup, where each task differs in the number of agents, there is no guarantee that the resulting agents can generalize to novel evaluation Markov games. So this is where we kind of, then they present the insights and objectives of our meta-representation for agents algorithm, which is, of course, to follow up on this model to make sure that you have something that works for meta reinforcement or meta-agent reinforcement learning, multi-agent reinforcement learning. Then there's this part, generalization by strategic knowledge discovery. So we want to be able to understand or discover the underlying strategic structures in the underlying games. Although the effective policies in the evaluation games are never known during training, agents can still learn the common strategic knowledge in different behavioral modes solely in the training games in an unsupervised manner with the imposed suboptimal game-specific knowledge. In particular, for population-varying games, the agents are assigned different strategic relationships. In other words, each agent pays additional attention to some agents while ignoring others. Instead of learning only one optimal joint policy, which we did in the previous example, training with multiple strategic relationships enables the unsupervised discovery of behavior modes, some of which offer appreciable returns in evaluation Markov games. Thus, when evaluating in novel games, the desired policy behaviors can be quickly generated by adaptation. In the extreme cases that sufficiently many strategic modes are captured, with an extremely large latent space, the desired policy for evaluation games can be directly found. So this is where they get into the mathematics of this and these mutual information between G and A conditioned on observation O. The variable M denotes the basic information of game M, such as the numbers of agents with each set of homogeneous agents. So you have this large latent space and diverse actions, and you have this diversity-driven objective that encourages high mutual information between G and A for behavior diversity, as well as between M and G to extract game-specific knowledge. Okay. So they do these experiments here. So they conduct experiments in 3 environments built upon the particle world framework. They cover both competitive and mixed games, including the treasure collection environment and resource occupation environment in a Pac-Man-like world. So this is where they kind of go through the experimental settings, and we won't get into that, but we will talk about some of these results. So there are benefits of game common strategic knowledge. You see that in these figures here. These are the figure 2 benefits of meta representations in 3 environments. So the first one on the left is the treasure collection game. The second one to the right are the resource occupation game. Then the 2 on the far right here involve the Pac-Man-like world. the graph on the left-hand side of those graphs is the results for Pac-Man, and on the right are the results for the Ghost. So you see there's an agent performing treasure collection at the left, and then the next graph over, we have an agent engaged in resource occupation, and then we have a Pac-Man-like world where we look at the representation of the Pac-Man and then the Ghost. And so we're looking at total executed episodes versus episode reward. And so let's see. We conduct our first experiments to show the benefits of the proposed method by demonstrating that when training in various Markov games, the game's common strategic knowledge can benefit individual training games. So in figure 2, we compared MRA and the following baseline methods. So they have these different algorithms that they use. The MADD-PG algorithm with relational representations, the reptile algorithm, baseline with the same network architecture as MRA, but agents and their policies only in a single MG, which is this baseline. So this is baseline, reptile, MADD-PG, and MRA. So you can see in treasure collection, MRA outperforms the others. In resource occupation, MRA also outperforms the others, and this happens after a number of total executed episodes. But early on, the MAD-DPG actually exceeds performance of the others in terms of resource occupation. In the Pac-Man-like world, we have a more heterogeneous result. We have the MRA outperforming the others in early on for Pac-Man, and then we have really, it's hard to see if there's a clear benefit to any algorithm in terms of performance later. For the Ghosts, however, we have this divergence of performance for the different models. The MRA outperforms the other models, and the MADD-PG model actually doesn't do very well later. So there are all these different, kind of applying these different models and comparing them, which is interesting because we're in different kind of game settings here. So for MRI and Reptile, the size of the training Markov game set M for 3 environments is 4, 4, and 3 respectively. The settings of the training Markov games in these 3 environments are as follows, and they talk about that. We note that the actual executed episodes of MRA in one Markov game are M times smaller than that for baseline and MAD-DPG, which reveals the efficiency of the proposed meta representation. So the number of executed episodes, if it's smaller, or if, there are differences in the number of total executed episodes, that can reveal the efficiency of the proposed meta representation. Comparisons between MRA and Reptile validate the effectiveness of MRA to meta represent effective policies in various Markov games. Due to the existence of game-specific knowledge, optimal policies in different games are distinct. Thus, in Reptile, using a unimodal policy to represent them all negatively affects their performance. So we don't, in some cases we want to use certain types of policies in some games, or in some, methods we don't. By comparing MRA with baseline and MAD-DPG, the benefit of the game common strategic knowledge for individual games is revealed. Since the baseline agents are trained only in a single game, they cannot benefit from such common knowledge, even with more episodes executed. The common knowledge helps MRA outperform MAD-DPG. We also evaluate MAD-DPG with homogeneous agents sharing parameters, which works poorly. Although the Pac-Man-like world is not a zero-sum game, we still provide cross-comparisons results for completeness. And this is where we have performance comparisons in multiple games. So in this case, we have, these are the training curves in figure 3 of Markov games constructed by varying the number of agents from the underlying environments. So we have these different games, and we have different numbers of agents. So what we can see is that as we increase the numbers of agents, it changes our results. So our different algorithms change their performance by adding agents into the environment. And so they give some other graphs here. They evaluate zero-shot transfer, and then they have some conclusions. So the conclusions are as follows. In this paper, we propose meta representations for agents that can generalize a Markov games of varying populations. With latent variable policies and relational representations, the diverse strategic modes are captured. As an approximation to a theoretically justified objective, MRA effectively discovers the underlying strategic structures in the games that facilitate generalizable knowledge learning. Our work opens up several new problems. Theorem 1 requires the computation as well as an extremely large latent space, both of which are impractical. Although approximations that MRA makes are reasonable, obtaining optimal values will not always be guaranteed. Possible future investigations include bounding by imposing restrictions on the evaluation set or enlarging the latent space size. With role-symmetric game settings, MRA has benefits in many research problems, including dealing with population complexity, overcoming the multi-agent random exploration bottleneck, and adapting faster with the meta-represented agents. A fruitful avenue for future work is to augment MRA by adapting roles to apply other game settings. Besides, achieving NE may not indicate global optimality in NeuroSim and Markov games. Therefore, we would like to explore different metrics such as social optimum and correlated equilibrium as future work. For population varying Markov games, we model game-specific knowledge as strategic relationship. Although it may lose the universality in broader scopes compared with general meta reinforcement learning algorithms, we hope the idea of explicit strategic knowledge modeling can inspire algorithms that adjust with the task. Okay, so that is this paper. Then there are two other papers here. This is the multi-agent learning for multi-robot systems. This is multi-agent reinforcement learning. And I'll just kind of go through the abstract of these, and then we'll have maybe a little discussion on this. So this talks about multi-agent reinforcement learning for multi-robot systems. This is a challenging issue in both robotics and artificial intelligence. With the ever-increasing interest in theoretical researches and practical applications, currently there have been a lot of efforts towards providing some solutions to this challenge. However, there are still many difficulties in scaling up the multi-agent reinforcement learning for multi-robot systems. The main objective of this paper is to provide a survey, but not completely, on the multi-agent reinforcement learning in multi-robot systems. After reviewing important advances in the field, some challenging problems and promising research directions are analyzed. So this is where they talk about multi-robot systems, where you need teams of robots instead of individuals. The performance of multi-robot systems in redundancy and cooperation contributes to task solutions with a more reliable, faster, cheaper way. So these are things like unmanned aerial vehicles, autonomous underwater vehicles, ground mobile robots, and other robot-based applications in hazardous and unknown environments. Okay. So the relevance to that here is that there's this emphasis on multi-agent reinforcement learning in this field. Multi-agent reinforcement learning allows participating robots to learn mapping from their states to their actions by rewards or payoffs obtained through interacting with their environment. And so multi-robot systems can benefit from reinforcement learning in many aspects. Robots are expected to coordinate their behaviors to achieve their goals. The robots can either obtain cooperative behaviors or accelerate their learning speed through learning. Among reinforcement learning algorithms, Q-learning has attracted a great deal of attention. There's also this idea of cooperative behaviors through an individual Q-learning algorithm, improving learning efficiency through co-learning, and K-cooperative robots learn faster than they did individually using this method. Basically, when you're using these kind of collective cooperative behavior approaches, you're basically sharing perception and learning experience, and that can accelerate the learning process within the robot group. Okay, that's the first paper, and then the second paper is this BIMRL, which is this paper, Brain-Inspired Meta Reinforcement Learning. And so this talks about their approach here. So sample efficiency has been a key issue in reinforcement learning. So we talked about sampling as part of the Bayesian approach. We also use sampling in meta learning, but sample efficiency, of course, is important in getting a proper account of the world, both in terms of the priors and of the observations. An efficient agent must be able to leverage its prior experiences to quickly adapt to similar but new tasks and situations. Meta reinforcement learning is one attempt at formalizing and addressing this issue. Inspired by recent progress in meta learning, or meta reinforcement learning, we introduced BIMRL, a novel multi-layer architecture, along with a novel brain-inspired memory module that will help agents quickly adapt to new tasks within a few episodes. We also utilize this memory module to design a novel intrinsic reward that will guide the agent's exploration. Our architecture is inspired by the findings in cognitive neuroscience that are relevant and is compatible with the knowledge on connectivity and functionality of different regions in the brain. We empirically validate the effectiveness of our proposed method by competing with or surpassing the performance of some strong baselines in multiple mini-grid environments. So what I found interesting about this paper is they kind of use the same approach that we talked about in the previous papers, but they have this memory module that's really kind of interesting. Aside from this reward, or they propose that there's this intrinsic reward to guide exploration. Aside from this reward, our memory module, which consists of an episodic part that resets after each episode, and a Hebbian part which retains information across different episodes of a particular task, gives us a performance boost in memory-based tasks, while helping deal with catastrophic forgetting that comes up in multiple task settings. So they have this reinforcement learning, this intrinsic reward part, which is the reinforcement part. And then they have this memory module. So the episodic part is basically where you get these episodic experiences. And you have this short-term episodic memory. Then you have this Hebbian part, which of course implements Hebbian learning, which is where you basically retain information by a sort of analog of synaptic plasticity. And this allows us to have this performance boost in memory-based tasks. Obviously, the Hebbian encoding and the experience of episodes can do that. It'll allow you to sort of avoid catastrophic forgetting. Sometimes when you switch between tasks, you get this catastrophic forgetting of the first task when you go to the second task. And it's a common problem in a lot of neural network systems, a lot of artificial intelligence systems. So having a strategy for that is important. This is, I guess, part of task generalization, where you have you switch between tasks, and you have to retain that representation of the original task. It's good if you have a meta representation, but if you don't, you have a representation for each of the tasks. And the question then is, do these representations interfere with one another? In other words, do you lose one representation when you build a representation for another task? So that's kind of why they're doing this. So their contribution is summarized as follows. They propose a multi-layer architecture that bridges model-based and model-free approaches by utilizing predictive information on state values. So each layer of our architecture corresponds to a different part of the prefrontal cortex, which is known to be responsible for important cognitive functionalities, such as learning a world model, planning, and shaping exploratory behaviors. So they have references for this. One of the objectives in this architecture is derived from our newly proposed factorization of the log likelihood of trajectories. So this says this is a technical variation on POMDP, which is where you have this predictive encoding ability of the brain that's taken into consideration. The second contribution is introducing a neuro-inspired memory module compatible with discoveries in cognitive neuroscience, which is the architecture I talked about before, where you have the Hebbian and episodic parts. This module will help in memory-based tasks and give the agent the ability to preserve information, both within an episode and across different episodes of some task. The design of this memory module is reminiscent of the hippocampus as the main region assigned to episodic memory in the brain. So it's hippocampally inspired, at least in terms of the way they describe it. Then number 3, proposing a new intrinsic reward based on our memory module. So the memory module is separate from the intrinsic reward. The intrinsic reward basically reinforces, I guess, the memory module. The reward does not disappear over time, is task agnostic, and is very effective in a multitask setting. It will encourage exploratory behavior that leads to faster task identification. Okay, so that's, and then they talk about Meta Reinformcement Learning, and this is kind of a review of how people do this. They use gradient and metric-based methods, and they define it there. Okay, so those are the papers. I know that was a long slog through those papers. Did we have any comments or questions if we want to start a discussion on
that? Excuse me. It's an interesting area. I don't know how much kind of go off on that. Again, it just reminds me that I'd really like to have Logan come talk about his work on multi-agent, reinforcement learning, where they're using LLMs. I mean, so it's LLM based, but they're developing a theory of mind to understand the other agents, right? So yeah. It's an interesting approach of trying to getting at that, how to cooperate, how best to cooperate, or how best to kind of coordinate. But yeah. Would this be coming up in with regard to the sustainable open source development? I mean, that seems like it was kind of, yeah.
Yeah, I mean, like, I don't know, BT put 2 of these papers in the Slack, so I don't know what the thinking is there. I definitely it fits into that area. And having a good model of, taking these results and kind of putting them into this context. Is, I don't know how they fit exactly. But I like the paper where they were talking about the different Markov games and thinking about that, because I've had this long-standing fascination with game theory and kind of like the things you could do with that in terms of learning and so forth. So that was a really interesting kind of approach.
Yeah, I had no specific context for putting it up, but I just came through those papers and read them. Like I just browsed through them, not very much in detail, so I thought I would share them in Slack. Yeah, and for the part where the Markov and the game part, I've come across this before when I was actually learning reinforcement learning for my previous project and applying it over there. So that's what you were doing. So I just felt like sharing it.
No, I mean, it's a great area, right? I mean, expands on MDPs, right? Like, I haven't seen, so, at least in most recently, the only time I see any discussion of MDPs is from Active Inference Institute. So I'm curious though now, just maybe if I've seen more of Daniel's work in terms of modeling and behavior or something like that, where you've got multiple agents, but no, this is it's a great area.
So it's interesting that if you remember Brian McCorkle, and he with the group a couple years ago, he built his summer of code project was applying POMDPs, partially observed Markov decision processes, to the open source sustainability project. And it was largely, in this case, it was like getting some code up and running to describe, applying it to groups so we could, flesh it out and put in parameters that were useful.
So, as well as using the Python version of, it was like Five Vista. What's the
Mesa?
Mesa. Thank you. Yeah. Right.
Yeah, I remember that. So that was, but we we kind of went further with the reinforcement learning that we did with the POMDP and with the different methods there from active inference. So that was like, kind of going through the tools that they have. And they have a lot of good tools, actually, for doing this sort of modeling. But, I don't know what the connection is necessarily between like MDP, POMDP, and reinforcement learning. I mean, obviously, in these papers, they kind of talk about it, but how would you do this for open source sustainability? I guess is the question.
Yeah. Well, I mean, again, this is the. I'll just post his GitHub in terms of, of course, Logan's approach is going to be very. It's going to be also using LLMs, but this is the. I mean, this is I think his most recent. Okay. And it gets at they're doing tasks, right? So I think you could definitely turn this into a software task, and I don't know how much theory of mind is necessarily useful, but but again, it could just be you know that kind of the framework for understanding the other agents, like how you're kind of trying to understand the other agents in this kind of collective action.
Yeah. Well, there was a little bit of well, they didn't call it theory of mind, but they were basically modeling an agent, like kind of a relative agent, where it was like observing its own state and then observing the state of its neighbor, and then like integrating that. So I mean, it's not theory. Because theory of mind implies that you have like a model of that mind directly.
Yeah. I mean, but that was but to some degree that was an ABM kind of approach, right? Like this perhaps maps better to a kind of software engineering team and its interactions. Did they have to work? Yeah. So they also limited the problem by doing things in a pairwise way, right?
Right.
So I mean, to some extent, they're not actually doing a Markov game. I mean, even though in the kind of ABM way, it's super interesting, kind of like the spatial and temporal dynamics that you can get from that.
Yeah. All right. Yeah, that looks good. Definitely a lot of kind of interconnections here between different methodologies and how to construct this sort of meta learning. And yeah, it's not an easy problem. I guess, like, people are kind of proposing with different techniques. Obviously, there are ways that we kind of more standard ways we approach things, and then we have to kind of put the pieces together to achieve this thing that's kind of elusive. Meta learning. How do you learn from learning? How do you synthesize different things that you've learned? How do you use observations from different agents if you're in a team or a group? And I guess meta learning is valuable both, kind of sometimes it's valuable for working with groups of agents. So, like, learning maybe what another agent is thinking or having this collective state. Sometimes it's useful for having this meta representation where if you switch between tasks, you don't lose everything from the previous representation. You can integrate the representations. So in the Markov games, the idea was that you had this sort of meta representation of the type of game. It wasn't like you were training it for every specific scenario and then you would call that scenario when it came up. You had sort of this, and I give you the rules of the game. You learn the rules, you learn what's possible within the rules, and then or maybe what's plausible within the rules, and then you act on that or you operate on that. And then, of course, we have this third type of meta representation, which is sort of, the statistical inference aspect, where you have the prior, the observations, and the posterior. And then, that's kind of, you have to have the right task structure or the right problem structure for that. And problem structure was an interesting thing that got thrown in there because we don't often think of that as like the defining factor. But if you think about like a Markov game, that's a very specific problem structure you can characterize as statistically. But if you were in like a more open-ended game where you had this heterogeneous aspect to it. You had different agents doing all sorts of different things, behaving in different ways. Then how does your agent build a meta representation from that? It's much harder.
haven't seen the continual learning community talking about multi-agent work. Although I did see that was one of those papers was from lifelong learning. So that's a continual learning group, right? Carl?
Lifelong learning?
Yeah.
Yeah, I think so.
Yeah. So they were presenting at a continual kind of
approach
conference. Yeah.
Yeah, I don't know. I mean, you'd think it would be like that sort of thing. I guess, like, the continual learning is hard enough, right? But yeah, I mean, so you have the multi-agent and multi-agent systems. I mean, if you think about it, they kind of are. They have to kind of be continual, I guess, because they're the whole point of having a multi-group of agents is have them interact and sort of perform these tasks in real time. So, like, if you had, for example, a swarm of drones or robots that did something collectively, you have to have this sort of, you can't train it on like a specific task and then get like optimal performance on the one task, and then they have to the task is really structured and everything, and then if they run into any contingency, then the whole thing fails. So you have to have this some sort of continual element. But yeah, I don't know the literature that well, but I'm not familiar with any work on it. So
yeah, it's ICLR is coming up, right?
Yeah, I think in the spring or summer, I guess.
No, I mean, I could is it? Okay.
Not sure.
I just started to seeing people.
Getting like acceptances and things like that.
Oh, is it not till? Yeah, well, it seems like people were advertising that they're, come see us. Yeah. So it's next week.
Oh, okay.
Yeah, April 24th. It's just like starting to see people saying like, here's what our lab's presenting at ICLR. Anyway, just always a good time to also just check what they've got in terms of like what workshops are they doing, tutorials, and, yeah.
What's the difference between ICLR and NeuroSim, like in terms of the types of work and the culture of the conference?
Yeah, I mean, it's a good question. I remember the French kind of communities that I was in, like always emphasized ICLR.
Yeah.
Like, and I think it just, I don't know if that reflects like did Bengio start this or something? Like, like I'm not, and I liked that during the pandemic they kind of they did the most to kind of like make their meeting online and like super cost accessible.
Yes.
But I feel like they've like, is any of this online
they gave
this year? And it's in because it's like it's in Singapore, right?
Oh,
so
yeah.
like really nobody should be flying that far.
Yeah.
I mean, yeah, but a lot of workshops, you know.
Yeah, I'll have to go over that and look at that and see what they're doing.
Yeah, but I you know, how do new conferences get started, right? Like what was missing from the previous this did start recently though, right?
I'm not sure.
Yeah. Okay. I mean,
what is the
and what does the top level domain CC mean?
I'm not sure. I think it's like
okay.
International domain. Yeah, it's. But I'm not sure what it means.
All right. ICLR. About. Okay. No, there's nothing useful here.
Okay.
Yeah.
Well, anyways, yeah.
Sounds like every other machine learning conference. Based in Wisconsin.
Oh.
Their contact address is in Wisconsin.
I guess just, isn't it learning representations, the LR part? Okay.
Yeah.
So maybe it's about like that aspect of it. I don't know.
Yeah, but I mean, it's like yeah. That's the bit that makes me think that it's like kind of post 2012.
Maybe
is that it's kind of, you know, deep learning ish.
Yeah.
You know, like this could have been previously. It would have been like feature engineering or something.
Oh, okay. Yeah.
But yeah. Yeah. Okay. So now I'm not going to have closure until I find out who started this meeting.
All right. Yeah, actually, Jesse's here, and I was wondering if Jesse wanted to give a short update.
Hey, yes, I'm here and I can speak. I'll speak briefly. I know it's kind of late in the day, but been a lot going on, and I haven't made the first parts of the meetings for a while. And I wasn't here last week, so just stop in and give an update on some things. So, one update that's pleasant. I'm officially, as of recognized by the dean of the school, I've completed my master's program. I haven't graduated, I haven't walked yet, but I'm done with courses, so that's great. But it's nice. I'll be in San Diego in June for graduation. So anybody who's around there, I'll try to be staying for a while, maybe a week or so, maybe a little more, depending on what else I can find out or get into there. So that's fun. So
are you not there now?
No, I'm in Boston currently.
Oh, okay. Because next weekend is the California Neurotechnology Conference.
Oh.
So it's the student neurotech conference.
I'm
going to be down here. Yeah.
There's so much. Yeah, there's so much more I want to do with UC San Diego, because I've got a lot of interesting projects coming up, and I have, as we sort of may recall, we've had a nice relationship with like excuse me, University of Albany, and I really want to follow that up. I visited the campus. Jeez, was that last weekend? Wow, I can't. I think it's true. Yeah, Nick Week was last weekend. I don't know for everybody else. For me, it feels like it's like 2 months ago.
Yeah.
And it was 7 days ago. Right now is about when it ended. But I was able to. It's a very difficult situation, but I could not attend a panel directly. and I spent hours and hours and hours coordinating it, having people come in and come out of the process. I believe Samantha Carollo, one of our interns, actually went to the panel as well. She was local and could make it. And that was huge. I'm going to be following up with her and do like kind of a I don't know, like kind of an interview with her and some other panelists too. I wanted to do more of that in person, but I had a situation where I could not attend at the last minute, and it was it was tough. But we had Kathy Parker, who was a longtime NICWIC like co-chair, step in to do the actual moderation panel. We had a lot of great feedback, and it's a very meaningful panel for me personally. Something I wanted to put on, and I'm very happy that it was useful. I've had good feedback from the panelists, and in general, I'm as pleased as I can be about it, and there's more to come from that. I was able to go to Albany, but I wasn't able to. I didn't get to have all the conversations I wanted to have when I visited. So there's a little more I want to do in terms of the upcoming like internships and summer stuff. I don't know if you want to get into this now, Bradley, or not, but like I have some ideas for like some of the summer cohort things, or even just writing up a little discussion about what the summer cohort is, because we all know and we've written about it sporadically and it kind of exists, but it could use a what is this thing now? And like it's an actual thing, and it's a lot of really nice parts to it. For those who don't know, it's Google Summer of Code, and also people who want to work on projects that didn't have the funding because Google's funding a number of slots is variable, and that's a whole other conversation. Google Summer of Code in the mentor emails that they have said like, hey, if people are asking you, well, it's like, well, we'll release all information at the time we're reviewing stuff right now. So if anybody's asking or you're getting DMs, I've gotten a few people like, hey, what's going on? And like, does it look like a lot of people apply to this? And say like, our mandatory response is we're reviewing all applications and we'll get back to you.
Right.
So just to clear that air, but the summer cohort is sort of Google Summer of Code. I think we finally settled on the name last year or so, or the year before, but it's Google Summer of Code proper. The people who didn't get funding that still want to do projects and be a part of our community, and also sort of this professional development open source meetings, which will start up again soon. I don't know if we've set a date for that.
Not quite yet.
Yeah, but like in the next few weeks, sooner than you think, our Friday meetings will be in full force again. It's actually warm out finally in Boston, the warmest day of the year I think here. So it's like it actually feels a bit more like summer, and that summer routine is coming up. In addition to the professional development stuff, I might add a segment, especially if I get a few interns on this front, to sort of I don't know if it's really a new project, but it's a new face on a project, which I'm calling Data and Direction, or Data X Direction. And I posted about it a little bit already, but it's sort of just, data science, data ethics, and a little bit of focus on sort of the tools, a little bit of focus on how they shape decision-making. Basically kind of some of my favorite things from my coursework. But then also like looking at papers and looking at things that are in sort of the more applied space, because I found one of the things I've found through my whole process has been kind of the intersection of data science, decision making, like society, ethics, tech. I say it's kind of a sister. I don't know if it's a project. If data and direction is a project of sorts, it's sort of under the general umbrella of like, I don't know, society, ethics, technology, or kind of group around that. And then also we talk about like data science stuff here all the time. We have the data ML channel. but I'm hoping to get a few people either through Albany, maybe through UCSD, or here, or just otherwise in general. Like I'm kind of first sorting things out with Albany currently right now, but I'm basically drafting up the final. Well, I'm finalizing the internship posting, and I'd really like to have. I think there's a nice dovetail to kind of include a little bit of that in the Friday meetings, or at least sort of. Another project that I'm working on is currently titled From Here to There, or Strategy and Mentorship for Innovators, which is basically super related to the I'll actually share my screen here really briefly. Whoops. I might not be able to, because maybe I can. Just a second. Okay, let me try this now. It's kind of a little. I haven't used Jitsi on this computer for a little bit.
Okay.
Bear with me here. But basically, just to really quickly show some of these things. Okay. This window. So I think, yeah. So a lot of the posts are here, starting to populate here on Substack. And I have a little brief intro post on what is success. But then we have the Google Summer of Code tips. We had first time learner panel. This is all related to the NICWIC. NICWIC panel was kind of inspired that, but I tried to distill some other things into it. This is a general post, but there's only 4 posts here right now, but there's like soon to be 10 posts here. Like there's a lot of here. This is going to be a lot of things being distilled into that we've talked about for years and years and years and years. Like, oh, I should write this down. I should write this down. I should do this. And so I'm doing a lot in this space. And currently, a lot of these are for early career things, but then I'm going to say more about like kind of I don't know, middle management, but people leading projects. Like, what is it like to deal with teams? What is it like to deal with the interpersonal stuff relative to achieving the short-term goals and all that stuff. So the sort of people leading the teams in the field doing the stuff, and then also the higher level vision setting, and how do you not be distracted. We've had a lot of things about like how do you at a very high level lead teams towards a specific outcome, and how does that look like in different fields of in a pure startup culture? How is that different in like academia? How is that different in when you're working in a very particular industry constraint? Again, like the mountains, monasteries, metropolis kind of comes into play there too. So those are like the higher level, broad visionary things. All of them I want to be kind of in the same place in, but we've talked about here a lot. So I'm very excited to sort of, I don't know if this is a hard launch, but somewhere in between a soft launch and a hard launch of this, and I'm starting to actually put this out. I put a little awkward logo that like the 3rd version I'm like finally okay with, and I have a lot more things from NICWIC to share here too. There's this whole sort of I'm trying to finish up all of that stuff as much as I can before we move on to other things in this space. And then for this one, there's only one post for data and direction right now. Ooh, and the page looks really awkward right now. Oh well. But this is sort of a really simple take on the data labels and data nutrition project. There's many more posts to be coming here too, but this is sort of a nice, hey, what's a tool, and like data labels are sort of this intermediary explanation about what's going on, or trying to convey something about the data set before you download it or play around with it. And there's implications for these other things, for transparency or reproducibility and all that kind of stuff. But there's more coming here too, and I'm going to be leaning into that a lot this summer. So I kind of have the nitty-gritty data technical stuff here, and then for this other thing, this is going to be higher level leadership, mentoring, strategy kind of things. Those are me two major foci, whatever, for me this summer. And I'm fortunate because there's time to write and time to make things and time to push all this stuff out. So there'll be a lot of movement on these fronts, and also like opportunities. I don't know, like Bradley, you and I are like, I'm gonna close this for a second. We've had so many discussions around this in the past. So I know this is all kind of like, ooh, I'm doing it now. But like anything you want to write about, or like, I'm kind of imagining some discussion series around it, all this kind of stuff that I want to do, like is there. And I don't know what you, I'm kind of just jumping this now, but we could talk about this in Slack or whatever else. But like, if there's anything that you want to cover or dovetail with some of your other, I know you have like a bunch of project management courses and things like that too. So however these can sort of dovetail existing efforts and further, like I really want to finally put to words all this. We've had so many wonderful discussions like on these Friday meetings that kind of are useful to people, and I'm hearing people ask, oh, what about this, and I'm getting these questions, what about this and what about that, and I was like, well, okay, like, we've had discussions about it for such a long time, and it's like I'm materializing it now. So I don't know, stay tuned for that, and for those who want to be involved in writing around those things or doing some of the posts or participating in some of the discussions, like you're welcome to do that as much as you want to. So yeah, that's an initial update. Any immediate questions or comments I can attempt to field?
Well, I mean, yeah, we have to start thinking about the content for our open source meetings, because the last couple of years we've done them, we've had, of course, the discussion about GSOC projects, discussion about open source practice, but then also some of these professional development things. So that might be useful to bring some of that into those meetings.
Oh yeah.
Yeah, and I think that looks great that like you have this, you're kind of taking a new dimension to some of the work that you've been doing with project management and applying it to data science and
and oh, go ahead, sorry.
Oh no, go ahead. It's
I mean I'm doing work in those spaces already, and I realize I want to do even more work in those spaces. So there's a double incentive for that for me, but also like particularly the last year, I have just had so little time to distill and write and generate things. I know there's a discussion to be had about like the Wednesday meetings and condition futures, which I may still put a little bit on the back burner and center some of these other projects as a lab discussion thing going forward. But like, I feel so relieved to not just be like vaguely talking about things, but writing them. And I also like, I appreciate, all of our efforts here, and I have a few efforts of people that have been doing some editing and thinking about stuff with me. And again, like the feedback and response from the panel and some of the interviews that I'm doing about this have been really, really promising. So I appreciate everybody's presence and past efforts that have led to these things happening now. And it's like, finally, I'm done with the coursework. I'm doing this other stuff. I'm transitioning in this way. And then now it's like, these things are starting to emerge that have been kind of just been sitting there for a long time. So yeah, let's have a, maybe, I don't know if you want to wait until next Friday or whenever, but like sometime soon, I think we could have maybe just a summer strategy meeting about open source, the summer cohort. Like, what do we want to say? Like, I already mentally have drafted the summer cohort post. and then we can just talk about that and say, what do we want to do? We have a couple months here, and I have some things that I'm going to be doing, which some of it will dovetail really well into this, some of it is separate, and then I know we have our plans, and we have a lot of great submissions too. So I'm excited about Google proper, and then the summer cohort at large. So maybe we can talk about that specifically. I don't know. I know we're kind of running out of time here today, but I think it'd be good to do that. Yeah.
All right. Yeah, it would be good. All right. So I think we'll wrap it up for this week. I think we had some good discussions this week. I'm looking forward to Jesse's work on the data science stuff and all that, and bringing that into our open source meetings. And we will next week we'll continue the discussions that we've been having this week on I think meta learning, and I did want to get into world models and the relationship between meta learning and world models, but I'm not going to do that I'm not going to get into that this week because it's quite a large discussion. So we'll talk about that next week.
Have you heard anything from like Adam Safron's, by the way? Speaking of world models,
no, I haven't heard anything recently. I mean, the paper was been submitted, and they I guess he got sick for a while, and then So
I've been talking with him, and yeah, he's been busy with things, and
so my last 7 months is getting sick and things happening. So I totally understand. I was just but yeah, like there's also like, I know we maybe saw a recap about other events that have recently happened. I can even say more about maybe next week I'll say more about the panel proper and what we're actually talking about at NAQUIC, but then also like other targets we want to hit this summer. There's a bunch of applications still kind of coming through, and some summer projects and programs. But yeah, let's talk about that in Slack, I guess.
Okay.
And thank you for everything else that's been going on. So,
yeah, sounds good. All right.
I had a good meeting with Neurotech at UIUC.
Oh yeah, really?
Yeah. They were very very interested in collaborating on some projects and expanding what their group does.
Oh, okay. I'm not familiar with it. Like, is that a student group, or is that like a...
Yeah. These are all our student clubs, or undergrads. But no, it was a good conversation.
Oh, great! Yeah, that sounds great.
And like a mix of cog and neuro kind of people, but also engineering, which strong tech school there.
Yeah. Oh yeah.
yeah. So anyway,
all right.
It was good.
Great. Thanks. All right.
Take care.
Take care.
Take care.
Bye.
Bye.